scalar equation of a plane. Everyone's still with me, yes?
Yep.
Yes.
Okay, just want to make sure. So scalar equation of a plane. All right, so when I say scalar equation, what's another word I could use?
Standard form, Cartesian.
Excellent. Cartesian equation or standard form, all meaning the same thing, right? Okay, good. So we have a normal there that you can see, A, B, C, normal vector. So normal vector means that it's perpendicular to the plane. Then we have P1P, which lies on the plane. So we're going to say, sorry guys, let me get my pen. Okay. So let P1, X1, Y1, Z1 be a point on the plane. And the plane has normal vector. ABC. Let P, X, Y, Z be any other point on the plane. All right. So if that's the case, then I know that the vector created by P1 and P is perpendicular to the normal vector ABC. So if I take the dot product, it should equal 0. Correct? And now I'm going to put it in component form. So P1P would be X minus X1, Y minus Y1, Z minus Z1, dotted with A, B, C equals 0. And now I'm going to perform the dot product. Okay, so I'm going to tell you what I'm trying to do here. I want to develop the scalar equation of a plane, or the Cartesian equation of a plane. So that's my goal here. So because I want to do that, I'm going to take what I need, which is this. The other values here. So here I've got negative A times X1 and negative B times Y1 and negative C times Z1. I can call those constants, right? Because we know that these are just values here. And so I can gather them together and make them constants and say that they are a constant. And I'll tell you the letter I'm going to use. Oops. And this right here now, I'm going to call D. And this is how the scalar equation was developed. Now, what do we know about Cartesian equations of lines? We know that ABC gives us the normal. Well, there's no difference with the Cartesian equation of a plane. Okay, A, B, and C represent a normal to the plane. Okay, so this is the equation now for a Cartesian equation of a plane, Cartesian or scalar. Okay. All right, so example 1. find a Cartesian equation of the plane passing through these 2 points, passing through -3, 1, -7, and has a normal of 2, 4, -5. So go back to what we did for lines. So when I wanted to find an equation, a Cartesian equation of a line, what did I do?
Use the coordinates of the normal to find A, B, and C.
Good. We know that this is just A, B, and C. And now, what can I do?
Sub the
Well,
point in. Sub the
I can-
point in.
Excellent. I can solve, sorry, do you see what I did here, guys?
Z instead of C.
You got it. Okay, so what I can do now is just sub in an X, a Y, and a Z and solve for D. And so I have -6 plus 4 plus 35 plus 3 equals 0. And what does D equal?
-33.
Good. And so therefore I know that the Cartesian equation is 2x plus 4y minus 5z minus 33 equals 0. So really no different than what we did for a line, except for now we have the extra variable D, which is our constant, rather than C being our constant. Okay? Okay, example 2. A plane has a vector equation, r is equal to 0, -2, 3, plus s, -1, 2, 0, plus t, 0, 3, -5. Find the Cartesian equation of the plane. What do I do? So right away, Cartesian equation, so what do I need?
The normal.
Yeah, you want a normal. I have 2 direction vectors. How can I find a normal?
The cross product.
The cross product. I have 2 direction vectors. If I cross M1 and M2, I will get a normal. So the normal equals -10 minus 0, 0 minus 5, -3 minus 0. There's my normal. And now this question is no different than what we did here, right? So now I have a normal vector, so I'm going to sub into A, B, and C. I'm going to sub in the point for X, Y, and Z and solve for D. Are there any questions?
I have a
Okay.
question.
Yep, go for it.
Yeah, how does finding the cross product find the normal?
What do you mean? When you do the cross product, you always find the vector that's perpendicular to both vectors. So if both of these vectors, S -1, 2, 0, and 0, 3, -5, if they lie on the plane, it doesn't matter. Like, we just know that they lie on this plane, right? So let's say they're like this. And I cross these two, then it gives me a vector that is perpendicular to both of them. And so I know that it must be perpendicular to the plane. That's
Okay.
what the cross product is, right? Yeah.
Yeah, thank you.
Yeah, no problem. Okay, so I have -10, -5, -3. So obviously, what am I going to use? 10 to 5. Sorry? No?
Those are
Okay. Sorry, I keep cutting you off. What did you want to say?
no, it's okay. Never mind.
I'm sorry. Okay. And now I'm going to sub in the point 0, -2, 3. What was the point? 0, -2, 3, I think, right? And yes, 3. Okay, what's D equal to?
1.
D is equal to 1. And so therefore, oh geez. Let's try that again. Cool. So same type of question as the first one, except we weren't given a normal, we had to find the normal. Okay? And so we did that by crossing 2 direction vectors. Okay, example 3. Given 3 non-collinear points, A, B, and C, on a plane, determine the Cartesian equation for this plane. So right away you see Cartesian equation, so what do I need?
Normal.
Always. Can I find normal?
Yeah. Yes.
Tell me how.
Any two of the points, because they're all on the same plane.
Will give me what? Normals?
The cross product of 2 lines, AB and AC.
You got it. So I went ahead and I found one normal vector, and this normal I got from AB. So I did B minus A. Okay? And then I'm going to go ahead and take AC. That's going to be my second direction vector. And so my second direction vector is 0, 7, and 3. Now, these are 2 direction vectors. And so now I have the exact same situation that I had here. I have 2 direction vectors and I have 3 points to choose from. So I need to cross my 2 direction vectors to find the normal. So normal equals 3 plus 7, 0 minus 9, -21 minus 0. Cool. Can that be reduced?
No.
No. Good. And now I sub in. Now I can sub in any one of these points and I am going to get the exact same value of D. Okay, Cartesian equations are unique, meaning there is only one, okay, for each plane. And so I can sub in any one of these points and I'll still get the same D. Did I get the right point there? I think so. It was -102. Oops. 9 times 0 is not 9. And so D equals positive 52. And so therefore, there's your Cartesian equation of a plane.
We missed. So for Cartesian equations, A has to be positive, right? Always.
Correct. Always. Always, always. And no integers. Sorry, only integers. No fractions or decimals. Okay, so let's take a look at some planes. So the first case that I have here, I'm showing two planes that are parallel. And what I'm trying to show you here is that if two planes are parallel, their normals are also parallel. Do you see that? In the second one, I'm showing two planes that are perpendicular. So I'm going to keep the color. So here is the normal to the red plane. Here is the normal to the blue plane. Notice that the normals are also perpendicular. Here we have intersecting planes, and they have normals. And I don't know if it's as obvious here. So here's one normal. Okay, here's the other normal. The normal of plane 2. Their angle here is such that cos of theta is equal to n1 dotted with n2 divided by the magnitude of n1 times the magnitude of n2. So what does that remind you of?
Dot product.
Yeah, good. Excellent. Geometric form of the dot product.
We missed. Is the angle, is it between the normals or is it also between the planes?
Well, that's what we're trying to show. So the angle between the planes will be the same as the angle between the normals.
Oh, okay.
That's what we're trying to show here. Okay, so why are we comparing regular direction vectors to normals or parallel perpendicular planes? Is because when we're dealing with the Cartesian equation, we want to be able to answer these questions using the normals. We don't want to have to find direction vectors. It's not necessary. So we're going to use the normals. Okay, so are the planes determined by 2x minus y plus z plus 4 equals 0 and x minus 2y minus 4z equals 0? They're both planes. Are they parallel, perpendicular, or coincidental? So what I need to do here is I need to find out if the normals are parallel, perpendicular, or coincidental. And then I can decide whether the planes are parallel, perpendicular, or coincidental. Okay, so what's my first normal?
2, negative 1, 1.
Good. What's normal 2?
1, negative 2, negative 4.
There you go. So I have two normals. Is one a scalar multiple of the other?
No.
What do you guys think? No. So what does that mean?
Not parallel.
Not parallel. Normals are not parallel, therefore planes are not parallel. Okay. How am I going to check if they're perpendicular?
Dot product.
Yep. So do the dot product here. Tell me if it equals 0. It does. So that means the normals are perpendicular. If the normals are perpendicular, so are the planes. What does it mean for two planes to be coincidental?
The same.
Exactly the same, one on top of the other. Okay, exactly the same. Good. What is the angle between the planes determined by these Cartesian equations? So we're looking for the angle between the planes, and so what we're going to do is find the angle between the normals. So finding the angle between the normals, we know that we do it by using the geometric form of the dot product. Okay, be careful there, guys. We're missing, there's no Z, and so it's 0. And so I'm just subbing in. Oops. Oops, oops, oops. 1, negative 1, divided by radical 3, 1 squared plus negative 1 squared plus 1 squared, and 2, radical 2. Okay. And so here, when I do the dot product, I get 1 minus 1 plus 0 over radical 6, which is just 0. And what is theta if codes of theta equal 0?
90.
Yep. Theta equals 90 degrees. So these planes were actually perpendicular. Cool?
When would the angle be obtuse? Because would it always give you the acute?
It depends. If you're solving for cos theta, would it ever give you? Only if it's negative, right? If you come out with negative, which I guess, yeah, you could end up with negative in your dot product.
Okay.
Right?
Yeah. Thanks.
Yeah, no problem. Okay, example 6. So calculate the vector and parametric equations of a plane with Cartesian equation. X minus 3y plus 5z minus 12 equals 0. So now I want to come up with a vector equation and a parametric equation of a plane. So for me to find those two equations, what do I need?
Two direction vectors and a point.
Yeah, I need two direction vectors and a point. So how do I find direction vectors? We need to find two direction vectors. In order for me to find two direction vectors, what do I need?
A point.
Yep. We need to find two direction vectors. Therefore, how many points? We need 3 points. Yeah. Okay. All right. So you can find whatever points you want. How would you find points on this line? Or on this plane, excuse me. How would you find points?
Sub in random values for x and y. Solve
Yes.
for z.
Exactly. Sub in random values, either for x and z, solve for y, or for y and z, solve for x. It doesn't matter, because as long as this equation is true, the point lies on the line. So I always like to make my life easy. And so what I'm going to find is the x, the y, and the z intercept. Don't have to, but it's easy. So to find the x-intercept, that means I'm going to let y and z equal 0. And so x is equal to, nice and easy, just look at it, x has to equal 12. So I have a point. Okay, let's find the y-intercept now. So that means x and z have to equal 0. So if x and z are 0, then I have negative 3y equals 12. And so y equals negative 4. And then to find the z-intercept, I'm going to let x and y equal 0. And so now what I have is 5z equals 12. And so z equals 12 over 5. Any questions so far? Okay, you can use any 3 points, guys. Doesn't have to be these ones. Okay, any 3 points. Okay, so now I need to find 2 direction vectors. So just choose any 2 of the points and subtract them. I'm going to use the first 2. And then my second. And again, guys, you can subtract whatever you want. It doesn't matter. Okay, now take a look at this vector. I did this one on purpose. Can I leave it like this, or should I leave it like this?
No.
No, we got to simplify it. So how can I simplify this? What should I do?
Times by 5.
Okay, yeah, I'm going to multiply everything by 5, or I'm going to factor out a 5. Oh, sorry, a 1 over 5, correct?
And then divide
What
by
else?
12.
Yeah, and by 12 as well. So it's like you're factoring out 12 over 5, right? Because they have a common factor of 12 in there. And so then what I would be left with is okay. All right, so my direction vector that I'm using is this. Okay, so now for a vector equation of a plane, I have any point using this one, any point you can use, plus s times one of your direction vectors, plus t times the other direction vector. S and t are elements of real numbers. So there is your vector equation. Now we want parametrics. So you guys know how to do this. 12 plus 3s plus 5t. Y is equal to s. And z is equal to negative t. Are there any questions? Okay. So I think that's our last example. This is repeat, same question, and here is the homework. So the homework is page 468, numbers 1 to 17, page 477, numbers 5AB, part 2 only, and there's your review. And there's a hint there for 15A. Are there any questions? No, everyone's good. So guys, there is a shortcut for example 6. It will be on the PDF when I post it if you care to look at it, okay? It's just a short way to find your vector equation, okay? And what it involves is just letting y equal the parameter s and let z equal the parameter t, sub in for it, and then you'll have your parametric equations very simply. And then from the parametric equations, you can get the vector equation. Okay, it will be posted in the lesson, okay? Are there any questions?
Which way is easier?
It depends. So if you understand